Okay, can you hear me? Yeah. So hello everybody, my name is Kostas Zoumpatianos. I'm a PhD student at the University of Trento in Italy, and I'm going to talk to you about query workloads for data series indexes. So this is joint work with Yin Lu from LinkedIn Corporation, my advisor Themis Palpanas from Paris Descartes University, and Johannes Gehrke from Microsoft. So we're interested in data in the form of data series, that is sequences of points which are ordered over a dimension. This dimension can be anything from time, angle, position, to practically any kind of ordered set of elements. So, for example, we have a lot of data which are ordered over time. We have time series, which are very common in financial data, for example, the prices of stock options or the amount of sales that we have. Web traffic data is time series, the amount of visits on websites. And health data, such as electrocardiograms, are inherently time series. Now, it's very frequent, especially in scientific domains such as astronomy, to order data over different angles. Scientists need to measure how variables fluctuate over different angles. And finally, it's very common to have data ordered over positions, and this is very frequent in genome data, such as DNA sequences, where the genomes are ordered over their position. Now we have big data. We have NASA's Solar Observatory producing about 1.5 terabytes of data each day, while the planned Large Synaptic Survey Telescope will produce about 30 terabytes of data each night. At the same time, each engine of the Boeing jet produces about 20 terabytes of data each hour, while the Human Genome Project already contains 130 terabytes of data. So analysts need to perform data mining tasks, such as classification, clustering, outlier detection, frequent pattern mining, and more. But in the heart of all this algorithm lies similarity search. They need to perform nearest neighbor and range queries. So in this work, we're interested in nearest neighbor queries, that is, finding the most similar data series to a given query within a data set. Now, in order to solve this problem, scientists have proposed methods such as indexing. And this can be broken down into two parts: summarizing data series using one of a plethora of summarizations, and building an index structure above these summarizations. This index structure can be either a spatial index such as X-trees or R-trees, or a specialized data structure for time series, or data series in general, such as ISACs, DS3, TS3, SFA, and many more. Now, the question that arises is which indexing method is the best one. Now, what previous studies have been doing was that they compared the performance of various indexing methods using random queries. These random queries have been randomly chosen from the data with or without the addition of some extra noise. Now, the problem with random queries is that we don't have any control of their characteristics. They're just random, which means that we cannot properly evaluate summarizations and indexes. Now, what we need is queries that cover the entire range from easy queries to hard queries. So we did some experiments with some previous data, and it turns out that most previous workloads are skewed towards easy queries. And this holds for DNA, electroencephalogram data, random walk data, and more data sets. Now, the problem is that if all queries are easy, then all indexes look good, while if all queries are hard, all indexes look bad. So what we need is a method for generating queries of varying hardness. So in this work, we propose the theoretical background for characterizing nearest neighbor queries for data series indexes, and then propose a method for generating query workloads in order to stress test indexes at varying levels of difficulty. So this is the outline of the rest of my talk. I'm going to start with some information about how summarizations and indexes work. Then I'm going to present to you our approach, some definitions, and our query workload generation method. And finally, I'm going to show you some evidence that our method works. So we're interested in similarity search, which means that we have to treat data series as multidimensional points. But the thing is that data series have many records, they have many points, which means a lot of dimensions. So in order to solve this problem, we usually summarize data series. We can use, for example, summarizations such as DFT, PAA, SACs, wavelets, and more. Summarizations are useful because they can be used by lower bounding functions in order to prune the search space. So let's say that we have two data series here, represented as two-dimensional points, P1 and P2, and we have a distance function which is defined between them. Now, using the summarized versions of this data series, we can provide some lower bounds for this distance, which is always less than the real distance. Now, these lower bounding functions are very useful because they are used by indexes in order to prune the search space. So this is how traditional indexes for data series look like. We build a data structure above the summarized data, and we store the raw data on the disk. Now, at each level of the index, we have summaries. We have summarized versions of the data that represent all the data below it. Now, by calculating lower bounds on these summarizations, if this lower bound is bigger than the solution that we already have, we can prune the search space. We don't have to go to the disk and check the real distances for this data. Now, the higher the quality of the lower bounds, the better the pruning. So the quality of the lower bound for two specific points can be measured as the ratio of the lower bounding distance over the real distance. So the closer this number is to 1, the tighter the bound is. And the average of this ratio over multiple points is called the tightness of the lower bound. So the bigger the TLB, the better the pruning. But still, some queries are harder than others. And let's see why. Let's say that we have multiple data series now, represented as points P1 to P8. And let's say that we have a nearest neighbor query Q. So we need to find the most similar data series to this query. And here we represent the distance to the nearest neighbor as min dist. And all the rest of the data series, they lie at a distance greater than min dist. So now, let's say that we have a summarized version of the data series that are not the nearest neighbor, that are more far away. So some of these lower bounds, they would look closer than the distance to the nearest neighbor. So these points, which are below the min dist, cannot be pruned, because we have to go to the disk, read the data, and dismiss false positives. So we use this intuition in order to define the minimum effort that an index has to do. That is the data series with lower bounding distance less than the min dist, the distance to the nearest neighbor, over all the data series. So the significance of this number is that when answering queries with larger minimum effort, summarizations and indexes will have to check more raw data on the disk. But the problem with minimum effort is that it depends on a specific lower bounding function, that is an index and the summarization together. So what we need, though, is a summarization-independent way of measuring query hardness. And in order to solve this, what we do is that we define an epsilon area around the nearest neighbor as 1 plus epsilon times the distance to the nearest neighbor. Now, the number of data series in this area over all the data series we define it as the hardness of a query. Now, queries with larger hardness tend to have larger minimum effort. This is because data series that are close to the answer have a higher chance that their lower bounding distance will be less than the distance to the nearest neighbor. So, as we've seen, random queries can have random hardnesses. But is there any way to generate queries of controlled hardness? So in order to solve this, we propose a 3-step process. First, we sample random queries from a given data set. Then we filter subset of the queries that have independent epsilon areas. And then finally, we densify these epsilon areas in order to reach some given hardnesses. The first step is trivial. We just split the data set into queries and data. And in the second step, we need to identify epsilon areas that can be independently controlled. So in this example, we cannot independently control Q1 and Q2 and Q2 and Q3 because their epsilon areas intersect. So we formulate this problem as a graph problem. We have one node per query and one edge for each pair that doesn't intersect. Now, what we need, our solution becomes the maximum click problem. So we need to find the maximum possible set of queries that are mutually non-intersecting. But because this problem is NP-complete, what we do is that we find a large enough click using a heuristic. Now, the third step is to actually identify how many data series we need to add at this epsilon area. So given a set of hardnesses as input by the user, we decide the number of data series to add for each query by solving a linear system of equations. Now, the last part of the problem was to decide where to add this data series in this epsilon area. So one way that one could solve this would be by choosing points at random in this epsilon area and adding noise to them in order to create new points in this epsilon area. But the problem is that we could have no or very few points in this area, or that we could have like clusters, which would practically do would increase the density of this cluster. We could produce more data, which could be close to the borders of this epsilon area, and we don't want that. So one other method could be to do one-n densification, and that is actually densifying the actual nearest neighbor. But there is a problem with that. So for bad summarizations, points with lower bound less than the min-disk can be located at very large epsilon areas. This intuitively means that points which appear closer than the nearest neighbor maybe have distances much larger than the nearest neighbor distance. They might be really dissimilar to it. While if you had good summarizations, on the other hand, points with lower bounds less than the min-disk tend to be very similar to the nearest neighbor. This means that they lie in small epsilon areas. So using one-n densification, we would end up putting both good and bad summarizations do the same amount of effort. And we don't also want that. So what we propose is equidensification. What we do is that we split this epsilon area into multiple zones, and we try to add the equal number of data in each zone, such as the worse summarization is, the more data it has to check. So this is our experimental setup. We have used 4 different summarization methods: piecewise aggregate approximation, symbolic aggregate approximation, FFT, fast Fourier transform, and discrete and wavelets, we're using 8, 16, 32, and 64 bytes. We have also used 2 standard indexes, such as ISACs and R-trees, and 3 different datasets: electroencephalograms, random walk data, and DNA data, ranging from 64 to 156 and to 1,024 points for each data series. So the first experiment was to check the different densification methods. So using all datasets with length 256 data series, we generated 100 queries using each densification method. And what we measured was the summarization error. So as summarization error, we defined 1 minus TLB. So a perfect lower bound would have a summarization error of 0, while the worst possible bound would have a summarization error of 1. And we also measured the minimum effort for a set of summarizations ranging from 8 to 64 bytes, both for PAA, FFT, DHWD, and SACS. So we normalized all this data over the values of SACS64, and it turns out that for equidensification, normalized effort is much closer to normalized summarization error, which means that the worse the summarization is, the bigger the effort it does. And then the next experiment was to see that actually our workloads had the hardnesses that we intended for them to have. And we were able to generate non-skewed workloads with, for example, the input here was to generate equal number of queries of 0.1, 0.3, 0.5 hardness. And our histograms are flat, which means that we actually manage that. And also, as we can see, we compare this to some random workloads, we can see that these workloads are skewed toward easy queries. And finally, we have tested the impact of some real indexes. We have generated 3 workloads: a random workload, we selected a subset of the random workload which had just hard queries, and we used also our equidensified queries. So it turns out that a designed query workload does not produce the same results as a random workload. So in random workloads, ISACs and R-trees were much closer to each other. So in conclusion, we have introduced a theoretical background for measuring hardness of data series nearest neighbor queries. We developed the first hardness-aware data series query workload generation method that works for any data series summarization and index, and validated using preliminary sets of datasets, summarizations, and indexes, which enables principled comparison of all summarization indexing techniques. Thank you.
Okay, thank you. Any questions? Okay. You mentioned that you needed to find out the maximum click, which is NPR, right? And you use the heuristic, right? Do you have,
so what we do is that we actually sort the nodes by their degree. So the more edges a query has, it means that it's more compatible with more other sequences. So we just add this to a set, and we continue this search like that.
Okay. So what is time complexity? Is it like?
It's a heuristic, so yeah, it depends on the data actually. It depends on the graph. Yeah.
Okay. Okay. Any other question? Okay. Thank you.
Thank you.